In Chapter 9, Segment 2, auditory signals run from the cochlea to the cortex. It says that there are about 30,000 to 50,000 auditory fibers from the cochlea that make up the auditory part of the vestibulocochlear nerve. The vestibulocochlear nerve, or cranial nerve 7, which runs from the cochlea to the brainstem auditory nuclei. Each auditory neuron responds to a precise frequency at its threshold, but for more intense stimuli, the neuron will respond to a broader range of frequencies. Tuning curve is a graph of the responses of a single auditory nerve, fiber, or neuron to sounds that vary in a frequency intensity. Even though an auditory nerve will transmit only auditory information, it does not respond to just one frequency of stimulation. The brain analyzes signals from thousands of hertz to calculate the intensity and frequency of each sound. Each auditory nerve fiber divides into two branches as it enters the brainstem, the cochlear nucleus and the ventral cochlear nucleus. They are brainstem nuclei that receive input from auditory hair cells and send output to the superior olivary complex. The superior olivary nuclei is a brainstem nuclei that receives input from both right and left cochlear nuclei and provide the first binaural analysis of auditory information. More paths also meet on the inferior colliculi of the midbrain, paired gray matter structures of the dorsal midbrain that receives auditory information. The outputs of the inferior colliculi go to the medial geniculate nuclei of the thalamus. Nuclei in the thalamus that receive input from the inferior cochlea and output to the auditory cortex. Neural response is frequency sensitive. The medial geniculate nucleus and auditory cortex are also inhibited by neighboring frequencies. All levels of the auditory pathway exhibit tonotopic organization. This is a major organizational feature in auditory systems in which neurons are arranged as an orderly map of stimulus frequency, with cells responsive to high frequencies located at a distance from those responsive to low frequencies. It begins with the cochlea. Brain imaging in humans show that many tones, noises, and other sounds result in activation of primary auditory cortex A1 located on the upper surface of temporal lobes. This is the region of superior temporal cortex in which auditory processing occurs. Speech sounds produce similar activation but end up activating more specialized. In pitch, information is encoded in two complementary ways. Minimal describable frequency difference is described as the smallest change in frequency that can be detected reliably between two tones. Frequency describes the physical property of a sound, meanwhile pitch relates to the subjective sensory experience of sounds. To distinguish pitches, there are two signals from the cochlea to inform the brain. Place coding is the encoding of sound frequency as a function of the location on the basilar membrane that is most stimulated by that sound. Treble is an aspect of pitch corresponding to the subjective experience of high-frequency sounds, especially musical sounds such as cymbals. Bass is an aspect of pitch corresponding to the subjective experience of low-frequency sounds, especially musical sounds such as bass guitar. Temporal coding is the encoding of sound frequency in terms of the number of action potentials per second produced by an auditory nerve. Pitch perception contains both coding, since they make up for each other's deficiencies. Sound is coded in two ways, according to the distribution of excitation among cells, place coding or tonotopic representation, or according to the temporal pattern of discharge in cells projecting to the auditory cortex. Mammalian species have a wide range of frequency in their vocalizations. Infrasound is very low frequency sound in general, below the threshold for human hearing at about 20 Hz. For example, some whales. Ultrasound is high-frequency sound in general above the threshold for human hearing at about 20,000 Hz. For example, bats. They process the vocalizations that are loud and ultrasonic to navigate and hunt in the dark. In brainstem, auditory systems are specialized for localizing sounds. The auditory system accomplishes the ability of identifying where a sound is coming from by analyzing two binaural cues. Intensity differences is perceived differences in loudness between the two ears, which can be used to localize the sound source. Intensity differences occur because one ear is pointed more directly towards the sound source, and the other ear has the sound shadow cast by the head, which prevents the sound reaching both ears with equal loudness. The head shadow is more pronounced for higher frequency sounds, while low frequency sounds have longer waves that reduce the shadow. And latency differences is differences between the two ears in the time of arrival of a sound, which can be employed by the nervous system to localize sound sources. One ear is always closer to an off-axis sound than is the other ear. There are two kinds of latency differences present in sound. Onset disparity is the difference between the two ears in hearing the beginning of a sound, and phase disparity is a continuous mismatch between the two ears in the arrival of all the peaks and troughs that make up the sound waves. Localization involves processing both intensity differences and latency differences. The duplex theory is a theory that we localize sound by combining information about intensity differences and latency differences between the two ears. At low frequency, there are virtually no intensity differences between the ears, no matter where the sound is presented. The time and arrival of the sound is the cue for sound localization. At high frequencies, a sound shadow cast by the head produces a significant binaural intensity difference. Birds and mammals have highly specialized brainstem mechanisms that can receive information from both ears and then use arrays of bipolar neurons to derive the sound and location from the left and right auditory signals. These neurons make very precise timing calculations by comparing the inputs to their two dendrites. Birds, the organization of neurons with their primary sound localization nucleus, constitutes an auditory map of space. Coincidence detector is a device that senses the co-occurrence of two events. In the mammalian brain, the superior olivary nucleus is the primary sound localization nucleus. The lateral superior olive is the process intensity differences, and the medial superior olive processes latency differences. Spectral filtering is an alteration of the amplitude of some, but not all, frequencies in sounds. Spectral cues and location are learned and calibrated during development. In the auditory cortex processes complex sounds, it says that the auditory cortex is specialized to determine and detect more complex and biologically relevant sounds, and evolved to process sounds of everyday life. Most cortical auditory neurons habituate rapidly to continuous tones, ceasing to respond after only a few milliseconds. Other cortical regions have rich interconnections with the auditory cortex. Two streams of auditory processing are found in the cortex. Dorsal streaming, which involves the parietal lobe, is concerned with spatial location of sounds, and ventral streaming, which involves the temporal lobe, analyzes the various components of sounds. An experience affects auditory perception and the auditory pathways. The auditory cortex's unique abilities come from the hardwired sensitivity that is fine-tuned by experience. For example, infants get experience of hearing complex speech sounds through exposure from family and other people. Experience with hearing aids has an effect on the ability of children to be able to localize sounds later on in life. Music is also effective in shaping the responses of the auditory cortex. The auditory cortex in trained musicians show a bigger response to musical sounds than it does in non-musicians. The extent of a musician's brain is extra sensitive to musical notes is correlated with the age at which they began training on music. Amusia is a disorder characterized by the inability to discern tunes accurately. This suggests that the rudiments of a musical sense are inborn. The auditory cortex that is involved with the perceptual analysis of music interacts directly with the mesolimbic dopamine-based reward circuitry of the brain to attach a reward value to music that is new. People with congenital amusia never develop the ability to understand the basic relationships of music, a problem with pitch and not rhythm. Brain imaging suggests that this is because the right inferior frontal gyrus, associated with pitch perception, contains less white matter in people with amusia. Diffusion tensor imaging is a modified form of MRI in which the diffusion of water in a confined space is exploited to produce images of axonal fiber tracts. Tone-deaf people have fewer connections between the frontal cortex and the temporal auditory cortex. And hearing loss is a major disorder of the nervous system. Hearing loss is described as decreased sensitivity to sound in varying degrees, while deafness is described as hearing loss so profound that speech perception is lost. And there are three main causes of hearing loss and deafness. It says that many severe hearing impairments arise early in life and impair language acquisition. The three categories of problems that lead to hearing loss and deafness include a failure of vibrations to reach the cochlea, problems with cochlear conversion of sound waves into action potentials, and dysfunction of auditory processing systems in the brain. In conduction deafness, it is described as a hearing impairment that is associated with pathology of the external ear or middle ear cavities. Ossicles become fused and can transmit sound vibrations effectively. There is surgery that may help to free up the ossicles in some cases. The nervous system is generally not involved in this form of hearing loss. Sensorineural deafness is a hearing impairment that originates from cochlear or auditory nerve lesions. It can be caused by noise exposure, metabolic problems, infections, exposure to toxins, trauma, or hereditary disorders. This hearing loss is usually permanent. Drug-induced hearing loss can result sometimes from the toxic properties of the group of antibiotics that include streptomycin and gentamicin. An oxytocin is toxic to the ears, especially in the middle or inner ear. Noise pollutions and loud sounds can damage the cochlea in a short period of time. Tinnitus is a sensation of noises or ringing in the ears. Central deafness is a hearing impairment that is related to lesions in auditory pathways or centers, including sites in the brainstem, thalamus, or cortex. It is caused by brain lesions such as a stroke. For example, word deafness is a specific inability to hear words, although other sounds can be detected. Another example is cortical deafness, which is a hearing impairment that is caused by a fault or defect in the cortex.